So the title of this talk is Unacknowledged Relativity Issues in Relativity Textbooks. Relativity textbooks are bad. They don't cover many of the basic stroke foundational issues about relativity. This gives false beliefs about relativity. I'm still using ChatGPT as my artificial intelligence that I prefer using, and thinking of it as Robert Einstein. I refer you to an earlier video. And that is being used to correct the mistakes that the human Einstein made. It does cover many other relative issues that special relativity textbooks miss out. So the question posed to the AI is, what things are not clearly acknowledged about relativity in special relativity textbooks and sort of general relativity? And ChatGPT says that's a deep and important question. Many standard relativity textbooks focus on presenting the theory in a clean, formal and mathematically elegant way, often avoiding deeper conceptual issues, ambiguities or open debates. So most textbooks are not going into the problems with the concepts, and they're not going into the problems where you could end up with ambiguities in understanding it, and they're also not raising issues so that you can debate things. Here are several key points that are often not clearly acknowledged or are downplayed in relativity textbooks. Number one, the role of convention in simultaneity. Einstein's synchronization method using light signals assumes the speed of light is the same in both directions. One-way speed. This cannot be empirically verified without already synchronized clocks, so it's convention, not a measurement. Many textbooks don't stress that simultaneity is defined by convention, not discovered by experiment, so they're letting students get a false idea about that sort of issue. Sort of like number two is the Lorentz ether theory is empirically equivalent, and often they don't talk about the Lorentz theory. The people teaching relativity often say, well, I'm here to teach relativity and not to teach about other theories. And the next issue, number three, is the dependence on coordinate choice, and that's time dilation, length contraction and relativity of simultaneity of coordinate dependent effects. They're not directly observable in an absolute sense, but appear due to the way events are described in different frames. Textbooks often present them as real effects without emphasizing they depend on the observer's coordinate system. So number four, relativity and GPS, subtle interpretations. Textbooks use GPS as a successful application of relativity, but often don't mention that GPS uses a preferred frame, and it's about synchronization and clock corrections are implemented in ways consistent with a global reference frame. This hints at something akin to a practical preferred frame, which contradicts the spirit of a full frame symmetry in special relativity. In other words, they might start teaching the students in relativity course that there's no preferred frame, but actually things like GPS do use a preferred frame. And issue number five is time dilation does not equal clocks running slower per se. A moving clock runs slow relative to a specific observer, but in its own frame it ticks normally. And time dilation is reciprocal. Each sees the other's clock as slow. Some textbooks give the impression that a moving clock just slows down in an absolute sense, which is misleading. But I think if you bring in the issue of a preferred frame, then you do have an absolute sense to it. So ChatGPT is not clarifying that issue very well. Number 6, the twin paradox often glosses over asymmetry. The resolution often appeals to acceleration, curved wheeled lines or space-time diagrams, but it doesn't always explain clearly why one twin ages less, given both experience the other as moving. The reliance on switching inertial frames is not always thoroughly examined. So basically, when they teach about the twin paradox, they don't often go into sufficient detail to properly explain things. And number 7, relativity may be incomplete or approximate. General relativity breaks down its singularities in sort of like things like black holes and is incompatible with quantum theory, so it has problems. There is no definitive experimental proof that space-time is curved in the ontological sense. It's a model, and so they don't explain that to students. What you're talking about is a model. Some physicists explore alternatives, e.g. emergent gravity, ether-like models, but textbooks often present general relativity as the final word, which is false. So number 8 is historical misrepresentations. Many texts simplify the history. They sort of portray the Michelson-Morley experiment as disproving the ether when it doesn't. And you also got the problem of what was Einstein aware of in 1905. And I've dealt with that in other talks about trying to work out what he was working from. And so these simplifications and the way they're teaching the history create the false impression of a sudden clean break. That's between what Einstein's talking about and classical Newtonian physics. And they present that a false impression rather than what it really was. It's a more gradual evolution. So number 9 points out that the conceptual ambiguities are still debated, and that is debated with people who are looking at that, such as philosophers of physics, but it's not debated in the relativity courses being taught to physics students. So what they debate is, what is space and time really, what are they really, and whether space-time is physically real or just a useful model. And then it goes on to how causality and locality work in quantum plus relativistic context, and those sort of things are still debated by these sort of philosophers of physics, but it's not presented to the physics students that these issues are still being debated, and thus giving the false impression to physics students that these things are not debated. So then number 10, alternative interpretations are underrepresented. Interpretations like the Lorentz ether theory, neo-Lorentzian interpretations, process theory, emergent space-time and shape dynamics, and so forth. It's all being missed out. So those ambiguities aren't just philosophical, they create cracks where alternative theories can take root. Here's how each ambiguity or unexplored aspect in relativity leaves room for reinterpretation, including ether theories, preferred frame models, and other frameworks that challenge or extend relativity. Number 1, simultaneity as a convention. That leaves room for absolute time. They don't go into that when they teach physics students. Number 2, this is LET, that's the Lorentz ether theory, equals SR special relativity empirically, and it's a different ontology allowed, so it's a different way of talking about things. it's supposed to be experimentally equivalent, and they don't go into explaining that when they're teaching physics students. Number 3, coordinate dependent effects. That means physics may be frame dependent, and they don't explain that. GPS is number 4, uses the preferred frame, and it's a possible practical ether, and they don't go into that. They miss all that out as well. So number 5, time dilation is reciprocal and contradiction if real. So if you've got two observers and each is saying the other person's clock is slower, that can seem contradictory, and they don't properly explain all of that when they're teaching to physics students. And number 6, twin paradox needs asymmetry, and it implies a hidden frame. So you've got, in the twin paradox, you usually got a twin going off in a rocket and then coming back to Earth and finding they have aged differently. They don't go into the problem of asymmetry and symmetry in such situations. And so the LET, which is LET, Lorentz ether theory, or other models can deal with things better. And so number 7, general relativity GR may be approximate, and that means that there should be maybe in ether gravity theories. General relativity breaks down its singularities and is incompatible with quantum mechanics. This opens the door to alternative gravity theories and involves a medium. That involve a medium, and you end up with these other things like emergent gravity. Number 8, there's historical myths, and you have revisionist theories have space. Once we recognise that the ether wasn't disproved and Einstein's 1905 ideas were part of a longer development, it frees us to revisit earlier ideas. And so often when they teach relativity, they are falsely telling you there's no ether, when really they should be looking into the issue of the ether. Number 9, philosophical ambiguities, and that leads to competing ontologies being allowed. If space-time is a model, not a physical entity, then other models, e.g. with particles moving through a medium, of viable alternatives. And what's listed there are some of the possible things there. So all of that is being missed out to the physics students. Number 10 is the suppression of alternatives implies intellectual monopoly. So when they're teaching physics students about relativity, they're not telling you about alternatives. And that given the false impression that there aren't alternatives when there are. So this is the summary of the things. You got ambiguity with simultaneity is a convention, and so forth. And LET, Lorentz ether theory, is empirically equivalent to SR, special relativity, and all these other things here. They're just not being gone into properly when they're teaching about relativity. And that's the end. Finished. Thank you. So this is the things that the AI has pointed out is bad in the teaching of relativity to physics students. Thank you.